Okay, I want you to start by explaining mammalian kidney function to your neighbor. I'm going to be adding things to the sketch as you go. Okay, so the whole thing starts with active transport, or rather the driver for this whole system is active transport of sodium and chloride out of the ascending loop of Henle. Okay, the ascending loop of Henle that I've labeled ALH here. Putting sodium and chloride out into the extracellular fluid and then into the blood. So that sodium and chloride are getting carried into the medulla. Okay, so keep going from there about all the different events that are going on, and I'm going to keep on adding to my sketch. Okay, so what's going on in the glomerulus? So blood is coming in. The glomerulus is a part of the tubule, part of the nephron that surrounds this ball of capillaries, the glomerulus. Capillaries are leaky. And the capillaries in your glomerulus have the highest pressures of capillaries anywhere in your body. So blood is coming in under higher pressure in those capillaries. They're leaky, so fluid goes out across the basement membrane. There's a basement membrane, so we're only getting small molecules: water, glucose, amino acids, calcium, sodium, chloride, urea, other wastes, and so on. So that's the glomerulus. Immediately in the proximal convoluted tubule, PCT up there, proximal meaning it's proximal, it's near to the glomerulus. It's convoluted because it is actually twisty. And it's twisty to increase the surface area. If it was straight, you would have less surface fewer cells to pick up, to reabsorb all these valuable molecules. So by being twisty, you get more cells, and it reabsorbs more material. Main function of the proximal convoluted tubule is to get back most of the valuable molecules. You get a few more later on in the distal, but most of it is happening here. And pretty importantly, in addition to recovery of glucose and amino acids with secondary active transport, calcium with primary active transport, and then water following passively. So you're creating a slightly higher concentration. I wrote about 300 milliosmoles. It actually would be slightly higher because you're pumping out these ions. Okay? And so water follows. So this is an area where you actually recover a fair amount of water and lots of valuable molecules. So already at this point, we have wastes that are more concentrated. Okay, urea and other wastes are more concentrated. Why? Well, think about it. We left all the urea behind, but we didn't take out only amino acids and glucose and sugars. We also had some water following. Right? So the urea and the other wastes are already somewhat concentrated. Not a lot, but somewhat. Okay? Okay, so we have, over on the right side here, we've got the blood. So the blood that has just picked up some of the water, a lot of glucose, amino acids, and so on, is coming over and running down in the opposite direction from the fluid in the ascending loop of Henle. So the blood is coming down, and we're adding to it sodium and chloride. Okay? So actively pumping out sodium, chloride will follow passively because of the charge difference attracted to the positive ions. And the blood keeps carrying it down deep into the medulla. Okay? So we're getting more and more concentrated as we go down deep into the medulla. These pumps in a human are capable of producing about a 200 milliosmol difference. In other words, about a two-fold difference when we're at 300 milliosmoles. So around here, inside, we might be 100, and outside 300. Okay, think through that and make sure it makes sense. So these pumps at any single location can create about a 200 milliosmol difference. Okay? So up here, it's going from maybe 100 to 300. Down here, 300 to 500. And the blood moving down is more and more concentrated. We're going to talk in a moment about why is it so concentrated inside the tubule. But does it make sense to you that if we keep moving 200 milliosmoles worth of salt out, this is going to get more and more concentrated, right? Does that make sense? And we're always carrying that down into the medulla. So down here, we're at something like 1,400 milliosmoles. And all along the descending loop of Henle, the cells have aquaporins. Okay, the fluid is coming from this area of 300 milliosmoles in your nephron. The blood down here is at 1,400 milliosmoles. Does it make sense to you that water is going to leave this less concentrated area and move into this more concentrated blood? Make sense? Okay, any water molecule that leaves is going to very quickly be attracted to a sodium or a chloride or some other dipole, some dipole. So it's going to get trapped. It can't easily go back because it's being held by the high concentrations outside. So it should make sense that water is going to be leaving. Okay, can we infer what the concentrations are going to be? Well, first of all, if water is always leaving, are the concentrations going to be always higher on the outside in the blood or higher inside in the tubule? Tell your neighbor. Okay. If we're always getting more concentrated fluid coming this way and less concentrated fluid coming this way, water is always going to be moving out to this more concentrated. So we're always going to have a slightly lower concentration in here. Katie? So is it going to be the same level of difference in the descending loop as the ascending loop? And there wouldn't be. In the descending loop, you might have 5, 10, 20 milliosmol difference at any given location. Because it's passive. And you're right, it's because it's passive. So down here you might be, and the exact numbers, I've never seen them measured, so I don't know. But if you had something like 800 here, you might be 790 inside. If you were 400 here, 390, and out here, okay, we might expect slightly lower concentration in the proximal convoluted tubule than on the outside. So if you want to change that to 290 to remind you. Okay. So we're always going to get movement of water out to this more concentrated area. Make sense? Okay. Okay, so by the time we get up here, we're at somewhere around 60 to 100 milliosmoles, and that's mostly wastes. We've recovered most of the valuable molecules. What's left up there is mostly wastes. Okay. The salt is valuable. Sodium and chloride is something that animals are often short on, terrestrial animals are often short on. In human history, salt has, as you guys know, has been currency at times. Okay, so all this salt that's in the descending loop here, once this water is coming out, we want to get that back. And here we get it back. Put it into the blood, get it carried away. This allows us to recover most of the water. So as you're sitting here, something like 25% of your blood is going to your kidneys. Okay, these little tiny organs. And a tremendous amount of the fluid is going into the nephron. If you didn't recover this water, you're recovering close to, certainly over 90% by the time you get down here, probably in the high 90s%. If you didn't do that, we would have to get up and head to the bathroom about every 10 minutes through this lecture to pee. Okay. So if you blocked these aquaporins, just imagine them blocked for a moment. Okay, and imagine over the next 30 seconds, you're getting the urge, the desperate urge to go pee, because so much fluid is staying in there. Okay? Chloe? So all the decrease is because of ions being pumped out. I'm oversimplifying a little bit down in this region, and I've left out one important part of the story that involves urea, but you guys don't need to know it to understand how it works. But if you take more physiology, you'll track what's going on with urea as well. Okay. So all of the differences here in the ascending loop, that's all pumps. Okay. Okay, other questions so far?
So the we're pumping the iron system to increase the concentration, the amount of fluid in the.
Yep, this is entirely, so if we didn't care about adjusting our urine concentration, if all we wanted to do was get rid of waste, you could just take the proximal convoluted tubule, connect that to the bladder, and that would be it. You'd recover the valuable molecules, you'd leave behind the wastes, put it in the bladder and let it go. The problem is we'd lose a lot of water. Now, if we were living in an environment with tons and tons of water, we wouldn't care. Amphibians don't bother with this, okay? So yeah, the whole loop of Henle, all this stuff is to recover this water, okay? And we could recover the salt just in a longer proximal convoluted tubule. Okay. Katie?
So if the aquaporins were blocked, how would that affect the rest of the function?
How would it affect the rest of the function of the loop of Henle? So if they were blocked, you would wind up with the same concentration down here as you had up here, right? So you'd have 290. So how big a concentration gradient could you get here? You could go from 290 to 200 milliosmol difference would be what? 490, 500, yeah, okay? So 490, 500, and that's the biggest concentration you could get down here. You could still get back to 60 to 100, but the highest concentration you could get down here would be something like 490, and that 490 is what would be sent back toward the heart. Not a good thing. Okay. You'd be sending highly concentrated or higher concentrated blood back to the heart. Okay? So blocking these aquaporins would be a bad thing. Liam?
What pushes everything through the system?
What's causing the movement of the fluid through? Yeah. So the pressure of the blood starts at going here. And in principle, that would be enough to get it partway through. We also know there's some tiny strands of smooth muscle around at least parts of this, and there's some rhythmic contractions that help to move it too. So it appears, I've never seen a good explanation of it, but it appears as though there's some, if you guys remember peristalsis, we haven't talked about it much, but peristaltic movements where you squeeze, 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 and you push material through. Okay, so that's clearly helping as well. But if you think about it solely as the pressure coming in, it's actually a bit of a misconception, but you'll still be okay. Okay? Okay. Okay, so what have we done? We've gotten waste molecules and valuable molecules, small ones, into the tubule. We've recovered the good ones, left behind the wastes. We've concentrated the wastes. So from here to here, we've concentrated the waste because we've been by about tenfold. Okay, we've taken 90% or more of the water out. So the wastes here are now somewhat more concentrated. Okay, and as we go up here, we recover the salt. So the wastes are still about 10 to somewhere between 10 and 100 times more concentrated. In the distal convoluted tubules, there are some wastes that get added. Okay, that actively get added. And now, in the collecting duct, this is the payoff for mammals. Has ADH been secreted? Antidiuretic hormone. Antidiuretic, a diuretic makes you pee. An antidiuretic makes you retain water. Okay, so antidiuretic hormone, if it's present, binds to ADH receptors, and that puts aquaporins into the membrane, and you recover ADH. Okay, so if ADH is secreted, binds to receptors on these tubule cells, collecting duct cells, that puts aquaporins into the membrane, here they are, and water comes out. Why does water come out? Why does it just stay? Okay, so it can be reabsorbed in the body. That's ultimate cause, and proximate cause, what makes it come out? Okay, concentration gradient. Remember, out here is, at this particular location, 900, 1100, milliosmoles, okay, and if we're at 100 milliosmoles, water will go out if it can, okay? So down here at the base of the collecting duct, at the end of the collecting duct, as urine is being collected to being sent to the bladder, we could have (60 milliosmol urine), or we could have about 1,100 milliosmol . Okay, if there's a lot of ADH, we can get up to 1,100. Why only 1,100? Why can't we get to 1,400? Any thoughts? Tell your neighbor why that might be. So this can be 1,400. If you let all that water out, is it having any effect on the extracellular fluid? Okay, what do you think? Anybody want to hazard a suggestion? Why not 1,400? Why 1,100? Gil, you want to try it?
I mean, you have the same concentration of wastes, but you've lost all of the salts. So, if I'm understanding what a milliosmol is correctly, then you have less solute overall.
So you have less solute, yes, relative to the water, right? If you're letting all this water out, okay, is the concentration of the extracellular fluid going to stay the same? You're going to dilute it, okay? And so you have less solute per amount of volume. You're letting the water out. Okay, so you can get that water out. Where does that water go? It goes into the blood. Okay, so that water is coming out. This is three-dimensional, right? So there's a blood vessel here. There's a blood vessel in front of it. There's a blood vessel behind it. The water coming out gets in here, but of course it dilutes this. So the most you can manage is somewhere around 1,100 milliosmoles. Somewhere around or a little bit higher than the concentration of seawater. You can't drink seawater because the problem is not enough of it is sodium and chloride. Too much of it is urea. And so that you can't get rid of 1,000 milliosmoles of sodium and chloride. You can get rid of a little over 1,000 milliosmoles of wastes plus sodium and chloride. We're only a little bit away from being able to drink seawater, but humans can't do it. There are other mammals that can get higher concentrations, and they can do it. Meg? So at the end of the ascending loop of Henle, so up here we're somewhere in the neighborhood of 60 to 100 inside the tubule. We're at about 300 milliosmoles outside the tubule. So there are no aquaporins in the ascending loop of Henle and the distal convoluted tubule. So we've pumped out all this sodium and chloride, so we have 60 to 100 milliosmoles inside, about 300 outside. Make sense? You are looking like you're unconvinced.
Can you phrase this in terms of not a milliosmol in terms of like solute concentration?
So milliosmoles is number of particles of solute. So osmolarity, if you put sodium and chloride in, if you put in 1 mole of salt, sodium chloride, you'd have a 1 molar solution of sodium chloride. You would have a 2 osmol solution, because each sodium and chloride dissociates into 2 separate particles. Okay, does that make sense? Okay, so milliosmoles, that's directly related to concentrations, and it's specifically about the number of particles per unit volume. Okay, and when we're talking about solutions in physiology, we care about the particles, not about what they were as a solid before they got put in. Okay, so 300 milliosmoles would be about 150 millimolar. Okay. Okay, Chloe?
Is there anything going on like between the ALH and DLH, like just in the white space in the middle?
So this is three-dimensional, right? So there would be a blood vessel. Actually, let me jump ahead because I have some images somewhere here. Okay, so this may help you see it three-dimensionally. I don't show this figure at the beginning because the orientation is, here's the blood coming in, okay? There's the glomerulus, here's the loop of Henle going down, and then the blood is wrapped around, and of course there would also be blood vessel on the other side of the loop of Henle. So each of these loops coming down in has a blood vessel here, and a blood vessel here, and a blood vessel here, and then another loop from another nephron, and another loop from another nephron, and so on. Okay? Does that make sense? Okay.
So it's like it's not drawn the same as it is.
No, I have drawn it here in order to show in schematic form what it would look like. But there would be a blood vessel here, there would be a blood vessel, there's blood vessels in between there, right, completely surrounding it. Okay, in the image that I put in the notes I posted, I actually put the blood vessel between these because I want you to realize it's both. Okay? Okay, so what would happen, one of the homework questions, what would happen if we clamped the blood vessel right here? How would that change the whole thing? So tell your neighbor, we clamp the blood vessel right there. How does this change? Okay, what's going to happen? So if we block the blood flow right there, what's going to be different? Gil?
Concentrations would be higher in the ascending loop because the salts can't move out.
Okay, so concentration is going to be higher in the ascending loop because the salts can't move out. So we're going to wind up with high concentrations here. So that's one thing. Liam?
The whole system shut down.
Will the whole system shut down? It will. So let's go step by step through and talk about why. Do you want to talk about the next thing that would happen?
Yeah, because the blood's connected underneath, like going back up the distal tubule.
Right.
The ascending loop of Henle also. So the salts wouldn't go out of the
Okay, so salt's never going to come out, so it's never going to get into here. So we're never going to change from 300. So the concentration is just going to stay at 300 milliosmoles. Okay, and so is water going to come out here? Nope. So the fluid will go through and just stay at whatever concentration it was here, carrying all the water and everything else out, and out it goes. Okay, so we're going to stop all that part. Now, we won't shut down excretion. We're still going to get excretion happening. Okay, but we aren't going to be able to concentrate the urine. All we're going to have is whatever happened here. Meg?
When you're actually pumping sodium out of the ascending loop, if there's no like particular concentration gradient happening between the blood vessel and the loop itself, would it just be pumped into the space and concentrated?
Yeah, so what would happen is at every location, you would pump The pumps would work until they had about 200 milliosmoles higher in the extracellular fluid than in the tubule, but it would never be carried away. So you would get to that point, and then at that point, the pumps are not going to be able to do anymore. The ions won't even get close to the pumps because the outside concentrations are going to be, well, actually what would happen is on the outside of each pump, you would have a sodium or a chloride you would keep binding back on. And so you would wind up with no net change anymore, so all the fluid that came through after that would just go through unchanged. Okay, so you'd wind up with around 500 milliosmoles all the way along here, and that would be it. But there's no blood movement to carry it away. Okay? Okay, make sense? If you drank more water, so if you drank more water, you'd be talking about, okay, more water is coming in, maybe a little bit more dilute, and so you'd have a little bit more dilute here, a little bit more water would come out and be carried away, and you would have ADH secretion, and you would not have, you would suppress ADH secretion, so you would excrete very dilute urine. The water is a waste product. Okay? By the way, this thing about needing to drink 7 tall glasses of water every day, myth, wrong. Okay? That came about because something like 80 years ago, a physician calculated how much water people took in a day, and he included everything, vegetables, fruit, meat, whatever it was, total water of what people were coming in, and calculated what the amount of typical intake was. And then in a little aside, he said, by the way, this would be equivalent to 7 glasses of water a day. This would be equivalent to 7 glasses of water a day. Years later, people said, you have to drink 7 glasses of water a day. It's a complete myth. Okay? You don't need to drink that much. Also, this idea that it has to be water, it can't be coffee or tea, myth. Coffee and tea, yes, the caffeine is a bit of a diuretic. You'll pee a little bit more, but it's still water coming through. You can still recover the valuable molecules. Doesn't matter what it is. If it's water, okay, doesn't matter if it's coffee or tea or whatever. So those of you who are drinking huge amounts of water and are kind of sick of it, don't worry about it so much. If you are a normal, healthy person, a good indicator of whether you are dehydrated is, does your mouth feel dry? Stop for a minute. Does your mouth feel dry? If your mouth feels dry, drink a little. If your mouth doesn't feel dry, you're not dehydrated. Okay, that's for a normal, healthy person. There are some medical conditions that can cause dry mouth or prevent dry mouth or whatever. Ivy? Does it mean you never have to drink water? That is correct. You could drink, well, I mean, you need it in some form, but you could have it entirely coming to you in fruits, in coffee, and tea, and other things. You don't actually have to have it as plain water. So what about kidney stones? So low intake of water is a problem because you're concentrating things in here. If you have a diet that's high in things that will crystallize easily, so a diet high in uric acid, you can get high enough concentrations in uric acid that it starts crystallizing here. And then kidney stones, incredibly painful. I've had 3 friends have them when I was there, and they were just writhing around on the floor in intense pain. My women friends who have had both kidney stones and gone through childbirth say that it's about the only thing that compares to childbirth. And so for men who want to experience what partners are going through later in life, for many of you, already happening for a few of you, if you want the men in your life to experience it, have them get kidney stones. Okay, blocking aquaporins we already talked about, so I want to just show you a few images of some of these. So here's the glomerulus, capillary coming in and blood going out. These little white things are little finger-like projections of cells. They're called podocytes, foot cells, and they help support the Bowman's capsule and the capillaries under these high pressures. But the fluid comes out through these gaps. Here's this leaky capillary. They have spaces between cells and little holes that would look like a donut hole through the cell, basement membrane all the way around it. So fluid is coming out. So large amounts of fluid are coming out. Here's a scanning electron micrograph, so what it actually looks like. So this is the podocyte. The capillaries are hidden underneath all these little processes. Fluid would be coming out through all these little dark gaps. into Bowman's capsule, the beginning of the nephron. The nephrons have Bowman's capsule in the glomerulus. They're all out of here in the cortex. They all have the loop of Henle go down deep into the medulla, come back out, and then the collecting duct, and here's the ureter down here. So it's this gray part. Blood coming in, and the renal artery, blood coming out in the vein, urine coming out in the ureter. Okay, and coming down to a bladder. Now, if you were a reptile or a bird, the fluid coming out of your kidney would be going into the latter part of your intestine. You don't bother with the loop of Henle. There is no loop of Henle in a reptile or a bird because they don't bother to concentrate their urine. They just use the proximal convoluted tubule to recover the good stuff, leave behind the bad stuff, put the urine into the intestine, and then the intestine reabsorbs the water. The uric acid crystallizes out, so it keeps going out of solution, and they can create highly concentrated dry feces. Okay, and that's how they're conserving water. Okay, any last questions before we switch over to temperature regulation? Okay, so that was homeostasis for keeping concentrations of waste and concentrations of valuable molecules at a steady state. There are lots and lots of other things that need to be homeostatic, staying about the same through time. And for all of these things for homeostasis, we have a series of some set point. So I talked about set points for glucose, okay, and for calcium before. We have sensory neurons or other cells that detect that set point. Integration neurons or cells, which can be the same. So the sensory neurons or sensory cells, they don't have to be neurons, can also be the integration cells. And then 4, we have effectors, something that affects whatever it is. So in all cases, we have a set point for something like X, which could be oxygen or glucose or body water or calcium or temperature. And there's a sensory cell that has some way of responding to a change. So for example, if it's temperature, as temperature rises, we might change sodium entry into a sensory cell. Or as body water changes, we might cause sodium entry to change into a sensory cell. So that affects some sensory protein, which could be a thermoreceptor or whatever. That changes the rate of action potentials. And will change the rate of action potentials in some integration interneuron. And that changes the response of some effector. So for example, at low temperatures, we might do something like closed potassium channels. We might do something like open sodium channels. So if at low temperatures, we get action potentials, right? Does that make sense? That would change the frequency of action potentials in some interneuron. That interneuron could also respond to others, so it can change the set point. Like let's say you've got an infection and you need a fever to help clear that infection. Not too high a fever, just a fever that increases temperature so that it's a little harder on the bacterium, but a little easier on your cells to get rid of it. So that integration interneuron can adjust what temperature you want, and then that can go to muscles for shivering. So the low temperature causes increase in sodium in, action potential shivering. That increases the temperature, and it decreases sodium entry. It's a negative feedback system for homeostasis. Okay, make sense? We've already done this for body water. So set point, shrinking of cells at about 300 milliosmoles. That causes the sensory neurons are ADH neurons. And if you don't have enough water, your cells shrink. They release ADH. They are also the integration neurons in cells, the same ADH neurons. They release ADH, and the effectors are cells with ADH receptors in the kidney that adjust excretion, and in the brain, cells with ADH receptors that adjust thirst. Okay? So if you don't have enough water, ADH receptors will cause you to retain water, and they will cause you to be more thirsty. Okay, those are the effectors. Does that make sense? And you should be able to do this for other things that we've talked about, like glucose regulation, calcium regulation, metabolic rate regulation. I want to add a concept here, the Q10 concept it's called. Q10, quotient 10, I don't know, for 10 degrees. And Q10 is simply the reaction rate at some temperature over the reaction rate at 10 degrees C colder. Okay, so it's how much does the reaction rate change. If the reaction rate doesn't change, Q10 is 1. Now, if we were talking a typical chemical reaction going between, say, 20 and 30 degrees or 25 degrees and 35 degrees centigrade, the reaction rates change by about a factor of 2 or 3. You increase the rate of random molecular motion, molecules encounter each other more often, they hit an enzyme or whatever it is more often with more energy, you double or triple the reaction rate. Okay, typical chemical reaction. In animals, that often does not happen. So in chemical reactions, in a test tube, in animals, if they have time to adjust, the Q10 is often about 1. So the key point is time to adjust. So let's say you get 10 degrees warmer. How do you keep a reaction rate constant? What if you decrease the amount of enzyme you made? So the heat is making the reaction rate go up, but you make less enzyme, keeping the reaction constant. That's one way. So animals change the amount of active enzyme they have. But that takes time. You either have to break down or add enzymes. That takes transcription or protein degradation. Okay? Another way to do it is to change the amount of substrate. Reaction rate goes up, but if you have less substrate, okay, then you can hold the reaction at a lower pace, the same pace as before. So changing reaction rates, or especially enzymes, that's how animals adjust. How many of you have had pet fish? How many of you remember taking the fish home and being told you got to put the bag in the water for an hour or so? Okay. How many of you didn't do that and killed your fish? Nobody went, oh, okay, we have 1 or 2 people who admit that. I did that once. I love tropical fish, still have them in my office. I learned. So you need to give them time to adjust. It takes an hour or so. Need time to ramp up transcription or degrade protein. Sometimes it takes longer. Okay. So that's the Q10 concept. Animals will gain or lose heat in an environment. So when you change them, animals will gain or lose heat. They have 4 possible responses. The 4 responses are: 1, they can tolerate it. Within limits, we tolerate changes in temperature. 2, they can adjust. So they can adjust the number of enzymes they have. They can adjust substrates. 3, they can move. Even bacteria will move away from an area that is warmer than their thermal preference to an area that is cooler, or the reverse if they're motile bacteria. Single-celled organisms do this. Okay? And of course, reptiles, amphibians, fish, all of them will do that. 4, an option that is often overlooked, they can die. The reason I put this on here is that I never used to put it on here, and then I would have an exam question that puts an animal in a thermally impossible position. And people would bend over backward to find a way to make that poor hypothetical animal in my exam question survive. I want you to know that may not be an option. It may be that in my exam question, this poor animal I have confronted you with, or even a human, is doomed. Okay? So that's the 4th option. Okay, how do you gain or lose heat? So I'm going to draw a bird. Standing on a branch. Okay? It's a bird, trust me. They can gain heat and they can lose heat by radiation. You radiate heat based on your surface temperature outward, and you gain it based on the surface temperature of everything around you. If the net around you is on average higher than your surface temperature, you'll gain heat. If it's lower, you'll lose heat. Okay, so you can gain or lose heat from the sun. That's 1. 2, conduction. The molecules in this bird's feet are bouncing around. That can speed up the molecules in whatever physically solid object it's touching. That's conduction, conductive. Or just something else that's touching it, even air or water. Okay? In completely still air or water, you're losing heat by conduction. Convection is when you add wind to that. And you might have relatively slow moving. Remember, heat is just random molecular motion. And warmed up, the air warmed up. Or water will also do convection. And evaporation why does evaporation cool animals off, or anything off? Well, water molecules are attracted to each other, right, by hydrogen bonding. So which water molecules would be able to get away? The ones that are moving really slowly, or the ones that happen to be moving really fast? The ones that get away are the ones that happen to be moving really fast. Those are the hottest molecules, right? So the ones left behind are cooler, less random molecular motion. So evaporation cools things off. Why is evaporation impossible for aquatic animals submerged in water? They're can't evaporate water. Okay, so it's not possible. So I've had exam questions where I asked about fish in hot water and how they can cool off. That's one of those thermally impossible situations. Put a fish in water that is too hot for it. What's it going to do? Which of those options is it going to take? Can it cool off by evaporation? No! It's got option 4, die. Okay, we'll come back to a couple of points next time. I hope to get to internal transport, but we'll have to start that on Monday. So Monday we'll start on internal transport. Mm-hmm.